Welcome back. Yet another property of determinant. If a row I of matrix A is multiplied by K and added to row J to form matrix B, then the determinant does not change. The same can be said about column I of matrix A is multiplied by number K and added to column J. So you recognize what we are talking about is row operation, elementary row operation. If you do this type 3 row operation on a matrix A, determinant does not change. Okay. Let's prove this result in the case of row operation. The proof for column operation is identical. Suppose A and B are rows, are matrices where B is obtained from A. How? You took I naught row of, I naught row of A. You're adding K times row M naught of A to row I naught. So that's how row I naught of B is obtained, okay? So B is obtained from A by an elementary row operation on A. So I naught row of B is I naught row of A plus K times M naught row of A. Okay. To calculate determinant B, expand along row I naught. So consider one particular term, I naught j, minus 1 to the power I naught plus j, determinant. So this is the I naught j cofactor of B. I naught j cofactor of B. Well, B I naught j is this quantity. All I have done is rewritten B I naught j. Now notice A I naught j, you can distribute this quantity here. Okay, so this multiplication distributes to each term. The first term is I naught j cofactor for A. And the second term, notice A M naught j. So you notice M naught here index and I naught index. So you are not synchronous. You are not maintaining the indices correctly. So when you sum along here, you will get 0. When you sum along here, because you have maintained indices, you will get determinant A. Okay. The left hand side, when you add these guys, you get determinant B. You see, indices are in sync. So this is determinant B. On the right hand side, you have determinant A when the indices are in sync. Whereas the second piece, here the indices are not in sync. So it's some other matrix, C, whose matrix is obtained by replacing row I naught of matrix A by K times row M naught of matrix A. So that is, they are not in sync, so you have determinant 0. In other words, determinant B is determinant A. Okay, we'll see a concrete example to understand this better. So here is matrix A, here is matrix B. How is matrix B obtained? I took K times row 2, added it to row 1. K times row 2, added it to row 1. Okay? It's an elementary row operation of type 3. Row 1 of B is obtained by multiplying row 2 of A by K and adding to row 1. Okay? Now use expansion along this. So first location, 1 1 location, its location sign, drop that row, drop that column, determinant of this, plus 1 2 location, its sign, drop that row, drop that column, its determinant of the leftover. Now 1 3 location, keep track of its sign, drop that row, drop that column, whatever is left over, its determinant. Okay, you are going to find this. So notice what happens. I am going to use first just the 9, 2 and 5 because by distribution I can do that. That fetches me determinant A. Now the K term, that is the determinant C. Look at C. You notice 4, -2, 3, they are repeated. So that gives me determinant 0. Okay, K times determinant D. Let's wait for this to go away. Yeah. First 2 rows of D are identical. Determinant of D is 0. Therefore, determinant of C is 0. And determinant of B equals determinant of A. So here is a good summary. When you interchange rows, determinant changes sign. That's the type 1 row operation. That's the type 1 column operation, interchanging of rows, columns. Determinant changes sign. Multiply a row by K. The K comes out. Multiply column by K. K comes out. So these are elementary row this was elementary row operation of type 2. This is elementary column operation of type 2. Now here is elementary operation of type 3. Multiply one row by some number, add it to another row. Determinant does not change. Notice here determinant change, here determinant changes, here determinant does not change. Same story with column operations. Determinant row operation of type 3 does not change determinant. Conclusion, use elementary row operations to find determinant of a matrix. So let's start with this matrix. Row 3, note row 3 and then row 1. Correct. Look at row 3. 3 is a common factor. I can bring it out. That was elementary row operation where I divided row 3 by 3, you see. Anyhow, the 3 came out. Agreed? Look at row 1. I'm dividing by 9. I get 1 there. 2 over 9, 5 over 9. So the 9 comes out. I'm using elementary row operation to get zeros at some location. Okay? 3 times 9 is 27. I'm trying to get 0 here. So -4 times row 1 plus row 2. That gets me 0 here. -4 times row 1 plus row 2, assuming my calculations are correct. -4 times row 1 plus row 2 here. No changes here. So far so good. I got zeros here. Now I need a 1 here. I can interchange these two rows. Maybe that's what I'll do. interchange row 2 and row 3. When you interchange rows, a negation comes out. A negation comes out and you got the one you wanted. I want a 0 here. So use elementary row operation of type 3. Multiply this by 26 over 9, add it to this. Got me a 0 here. 26 over 9 times this, add it to this, I get this. Okay. Now, what we now have is an upper triangular matrix. What do we know about upper triangular matrix? Determinant of an upper triangular matrix is product of its diagonal entries. So determinant A is negative 27 times 1 times 1 times negative 5, 135. Okay. This method of computing the determinant is called the method of reduction to triangular form. Okay. Let's come to this in our next video.